Coreform, together with Greg Vernon, Director of Product Management at Coreform. And this is the third webinar we've had over the last few weeks with our latest release of Coreform Cubit. This is a big release for us, where we're introducing U-splines commercially for the first time. So with this webinar, we're going to go into more of a deep dive about how to create U-splines and export them for use in both Coreform IGA and LS-DYNA. So if you just want to go to the next slide for the agenda, Greg. So this is definitely more of a working session. If you want a high-level overview, you can reference the webinar we gave a couple weeks before. But today we want to really get into the details to show you how to use U-splines, talk about the current limitations, and how to actually use it to create models to take advantage of isogeometric analysis capabilities, both in ANSYS LS-DYNA as well as Coreform IGA. So we'll have a lot of demo in this webinar. As always, this webinar will be recorded. Feel free to ask questions liberally throughout the webinar through the Q&A, and we'll either type back the answers or have Greg answer those live. So with that, let me turn the time over to Greg.
Good, thanks, Matt. So as Matt said, this is going to be a bit of a working session. So I'm going to be flipping back and forth between the presentation and Cubit. So if at any point, if the screen recording cuts out, just let me know and then we'll get it fixed. So let's start with just talking at a high level, just again, what are the benefits of U-splines? The benefits of U-splines is that they enable a tight CAD connection between the U-spline and the actual B-rep in your CAD model. They allow for a greater accuracy per degree of freedom, which allows you to solve complex problems on less hardware, faster, and smarter. And that goes hand in hand with being more efficient on its compute and more efficiently utilizing your computing resources that you do have. And then finally, they also enable our Coreform IGA solver with its calibrated speed and accuracy that it provides to the finite element practitioner. And just what are U-splines at a high level? What they are is, you've probably heard of B-splines and NURBS and T-splines. U-splines are smooth splines over unstructured meshes like the one you see here. So mesh layouts that are not able to be done with single NURBS patches or a single B-spline patch, we can do with a single U-spline on these complex unstructured meshes that are pervasive in real applications. You can also use U-splines in third-party solvers, one of which we're going to talk in depth today about. But just, you're going to hear some terminology. And just so you know, there's a technology called Bezier Extraction, and it is the technique that enables traditional FEA solvers to utilize spline elements like U-splines or T-splines, B-splines, and NURBS. ANSYS LS-DYNA supports Bezier Extraction via what's called a BEXT, or sometimes they'll call it BEXT file format. And the BEXT takes its name from Bezier Extraction that I've highlighted here in bold. So just when you see BEXT, that's what this is saying, is it is that Bezier extraction technique that's allowing ANSYS or these other third-party solvers to utilize U-splines. And so if you find a third-party solver that we haven't mentioned that supports BEXT or Bezier extraction, it can then support U-splines, in principle anyways. As I mentioned, Coreform Cubit supports exporting to LS-DYNA through this BEXT file. And we're also collaborating with both Sandia and Idaho National Laboratories to support Bezier extraction, both in Sandia's Exodus mesh format, which is used by Idaho National Labs' Moose FEA code, which is an open source finite element code. We won't talk about those in this webinar today is that is still work that's ongoing, but we are excited to get that capability. And once we have that, we'll have another webinar to discuss that in more detail. But you can Google around and find more information about this on the internet. So then at a high level, before we dive into the demos, there's kind of a general workflow in Coreform Cubit for building U-splines. And I want you to pay attention to the bold letters that I've got here: mesh, set, build, fit, and export. I bolded the commands that are Cubit commands, or at least that start the Cubit commands. And this is your general process that we're going to mesh our geometry with hexahedral or quadrilateral for surfaces with these elements. We're going to then set the U-spline properties on the geometry that we've meshed. We then build the basis. And then there's this other concept of now fitting the U-spline to the CAD geometry that diverges a little bit from traditional FEA, which uses these low order elements that interpolate the geometry, and there's no need to fit. In our case, what we need to do is a technique called Bezier Projection. An example I've shown here on the right, well, you can think of it as, imagine that this black curve is your CAD model. And then we say that we're going to use maybe a quadratic U-spline with its Bezier components. And we're going to then fit those elements as closely as possible to that input CAD model. And that process is called Bezier Projection. As this is still a new capability in Coreform Cubit, you will sometimes notice that some settings or some U-splines you might build, they may exhibit a poor fit during this stage. And if you do encounter those, we encourage you to send us your model to our support group so that we can fix any lingering issues that happen there. Once that's finished, though, we're then ready to export to the desired format and then use that in either in Coreform IGA or something like ANSYS LS-DYNA. So what I'd like to do now is maybe right before I dive into the demonstration, I see that there's maybe a couple of chat questions. So Matt, I'm just going to ask if there's anything that I should be answering before we move on.
No, proceed.
Okay. All right. So what I'm going to start with is an example of building a volumetric U-spline on this knuckle geometry, which is one of the example problems, or one of the example geometries that come with Cubit's tutorials. And we're going to take a traditional body fit meshing approach with hexahedral elements, which means that before we even mesh, we're going to defeature our geometry and partition it for meshing. So a couple things I'm going to do is I'm going to defeature away this fillet, this chamfer, as well as this small fillet here, this chamfer that's on this surface. And then we're also going to use virtual topology to composite away this small surface with the slivers that it introduces. So to do that, I'm going to go to the Mode Geometry, Surface, Modify, and Remove. I'm going to use this default Extend option. I'm going to select this chamfer surface. I can actually right-click now and say Select Similar Surfaces, which has automatically found the chamfer on the other side as well. And I can then apply to remove that feature. I'm going to do the same over here now with this fillet, with the same extend option. And then I'm going to do it with this chamfer and extend. I'm going to wait to do virtual topology until the very last stage. Anytime you do virtual topology operations, which you will be able to tell if an operation is real, you won't see when it's virtual, Maybe I'll show you what you see when it's virtual. There's a little box here that will say virtual geometry. If you see virtual geometry, that means it's going to apply virtual operations. And that can reduce some of the robustness of downstream applications. So I recommend only doing virtual geometry at the very last stage. But now what we're going to do is we're going to partition our geometry. So I go into the mode geometry, entity volume, and then the scissors for web cutting. So it's going to cut our geometry. What I'm going to do first is I'm going to cut off these prongs. So I'm going to cut volume 1 using a plane from this curve. So I'm going to use this curve near this vertex, previewing that cut. This is the cut that's going to apply. I'm going to then cut off the shoulders by cutting this volume 1. Again, a plane from curve. So this curve at this vertex, so that plane to cut this shoulder. And then this plane over here. The last steps I'm going to do is I'm going to now cut my geometry into quarters. And so to do that, I'm going to again cut plane from curve, all volumes. So I actually right click here and say select all. This curve by a fraction at its midpoint. So I'm going to cut it down the middle like this. And then lastly, again, all volumes, but now choosing this curve at its midpoint to apply this cut. Actually, I have one more cut that I'm going to do, or two more cuts I'm going to do, is I'm going to now extend this circular surface through this geometry. So that's a sheet extended from surface on these 4 volumes. And then I'm going to cut this volume so that it's trimmed at this surface. So I'm going to trim all 4 of these. My plane surface. So now I've decomposed my geometry. I'm going to now apply virtual topology operation through this surface composite. I'm going to select these surfaces, right click, select similar. And now I selected all of those. And you can tell that it's virtual because it's now a dashed line instead of a solid black line. The next step is to imprint and merge the geometry. So we have a conforming hexahedral mesh. So imprint merge volumes. I'm going to select all. And now this geometry is ready to mesh. Now, one limitation in this version of Cubit, which is 2021.1 or 0.11, is that we only support U-splines on swept volumes. We don't support maps, or if we look at the different meshing schemes we have for solids, we don't yet support map or submap or tet primitive, sphere, or polyhedron. We are working on those, but sweep was the most general, so we've done sweep first. We are targeting the rest of these options in the next release of Coreform Cubit. So this is a temporary limitation. What I'm going to do is I'm going to just apply, I'm going to tell Cubit, just try to automatically select the source and target for all of the volumes. So I'm going to say apply and mesh. I'm going to actually use a coarser mesh here. I think I want to use a mesh size of, maybe let's do 4. So approximate size for all volumes. Let's preview. Yeah, let's do a mesh size of 4. So this this is the initial hex mesh layout. Similar to traditional workflows in Cubit, if you wanted to have, say, a structured, like more of a structured layout here, to remove these extraordinary points, which we can't build smooth bases on, you could set the surface mesh schemes as well. So if I delete this mesh, I can assign a surface mesh scheme of, say, map to these surfaces. And now when I mesh volume all, I might have to I mesh those first, don't I? So apply the scheme and then mesh it. Now if I mesh all the volumes.
Greg, your initial partition, you have more cuts than you would strictly be necessary for the hex mesh. Why do you have, like, for instance, like, why did you quarter the model?
I quartered the model because I knew that if I quartered the model that I could guarantee getting a nice structured meshes on, say, this surface. So I did it primarily because in traditional hex meshing workflows, you try to build as much structure into the decomposition as possible. And that's oftentimes done through web cutting further. But you are right, I did do more cuts than were necessary. And that's a very astute observation. But that's why I did it.
Okay, thank you. That was an observation from Randy. So thanks, Randy.
Yep. I will say one limitation also in this version of Cubit is that between each of these volume boundaries, they are only continuous, not smooth. And that might be a reason why you may not want to do all of this partitioning in this current release of Cubit, because it does introduce decreases in continuity that you may not want. So that's a reason not to web cut as much. It's a implementation detail that we're also working to mitigate. So now what we can do is build the U-spline. Now you recall, if I just pop open my plot or my PowerPoint, we don't yet have a GUI workflow for building the U-spline. Our strategy at Coreform is to add functionality through our command language first and really nail the user experience at the command language level, and then develop the GUI interface, the GUI interactions for the users. So today you have to use command line options or command line executables. So what we're going to do first is we're going to set the U-spline properties on the geometry. I'm going to also mention that if you type a question mark as you type a command, so if we say type set U-spline, and if you forget what the rest of the command is, on my keyboard, if I do Shift and then the key to do a question mark, it will complete the command for me. I could also type help set U-spline, and that will also print out documentation. And so that's really useful for when we don't have a GUI component yet to be doing these commands, to help yourself see how these commands work. So we're going to set the U-spline on volume all. We're going to tell it that we want the degree to be degree 2, and the continuity to be, the maximum continuity is degree -1, which would be, so 2 minus 1 equals 1. So that's going to be our maximum continuity that we're going to request. Again, we have to drop continuity at some interfaces due to current limitations in our implementation. The default is what you see here, degree 2 continuity 1. So you don't strictly need to set that for this model, but it's good practice. Now that we've set that, we're going to build the U-spline basis. So to do that, we're going to say build U-spline. I'm going to hit question mark here. So it's going to be build U-spline volume the IDs, and then we're going to tell it what U-spline ID we want to give it. So you build U-spline volume all as one. So I can put any number in here if I wanted to, but that's how I'm going to refer to this U-spline in the later commands. So I'm going to call this, actually maybe for this, I'm going to call this 101. Just so you can see where I refer to that U-spline ID later. So now the U-spline's built, it has given us a warning, which we'll see later on this. There are some kinks or creases that will not be creased in the spline. And we'll see where that comes in, and we'll see how to work around. Next, we're going to fit the U-spline using Bezier Projection. So if I type fit U-spline, do question mark again, we're going to tell it U-spline 1, 0, 1. And then you don't need to worry about this tessellation tolerance. There are better ways to handle this. So I would just recommend doing fit U-spline and the ID of the U-spline. It will print out errors that are more just warnings that when you're going out to codes like ANSYS, since we don't yet have a GUI interface for printing out element quality, this would be the element quality for some of these hexahedra that a tool like ANSYS would perceive. Coreform IGA doesn't perceive the scale Jacobian in the same way that ANSYS does. But that's going to be important for ANSYS. Now that it has finished tessellating and finished doing this fit, on our view bar, there is a new icon that looks like a cube with like a line down the middle. And if you hover over it, it says show U-spline view. And that plots our U-spline. We're working to make this visualization a bit more seamless. It requires a few upgrades that we need to make. But for now, that's how you will visualize the U-spline. Now, what you'll see is that there is this warning about some edges not being creased. And we can see that right here on this part of the geometry. That there's a crease here that has kind of been filleted over. And again, this is that Bezier projection. The basis that was built is treating this as smooth. And so then with a smooth fit to a sharp edge, this is the closest fit that those elements could get. This is a current implementation detail that we're working on, but in 2021.11, there's a few workarounds to ensure that you'll get a crease there. One, so what I guess what I'm gonna do now is, if you built this U-spline, the next step would be to export this U-spline. So similar, export U-spline. You would tell it the ID is again 101. And then there are options for the export. And you'll notice that one of these is BEXT, which is the format we're going to export for LS-DYNA. You can also export just the surface to Visualization Toolkit or VTK file. You can visualize in pair view. We are working on a new specification of Bezier extraction within a JSON format. And then I mentioned we're also working with our with some collaborators at the National Labs to support Exodus. So those are the ones I would focus most on. But we would export as BEXT. Tell it the file name that we want. So we might call this like knuckle U-spline. And then if we were exporting to LS-DYNA and we'd assign boundary conditions, we'll show this later, but if we were assigning boundary conditions and side sets, we would want, there's a workaround for what DYNA is expecting, that you would feed it this DYNA cards parameter. And so that's what you would do to then export that U-spline to an external code. Now, to address this shoulder creasing, let me go ahead and import just that shoulder. So there's just going to show on this just the shoulder by itself, a couple ways to get a crease there. One way is to partition the geometry, again, to have a cut here, because along a cut, we're going to have only C0, which is only continuous, not smooth. So to do this, what we might do is we might partition these curves, or split these curves by the point closest to this vertex. And so it'll create these two vertices. And then we can create a curve between 2 points. So let's create a new curve or a new line between this vertex and this vertex here. Oops, I lost my, there we go. And we can then cut this geometry by sweeping this curve through. And we could sweep through, we could also do a loft through, but I'm just gonna, just for speed here, or expediency, I'm just going to sweep this curve. Sweep curve this volume. Let's sweep this curve along this guide curve. Oops, got the wrong curves here. Curve 6 along 20. There we go. And so you can kind of see that cut that is going to make here for us. So if we do this cut, and now if we imprint and merge, now when we do our, I'm just going to do all size 4, all size scheme sweep, mesh all. Draw my mesh here. And maybe we'll do a little bit finer mesh, delete mesh. Do a size of 2 here. So now if I build U-spline, set U-spline, vol, all, degree 2, continuity 1, build U-spline, vol, all as 1. And then fit U-spline 1. We'll now see that we've now captured that crease, and the fit is much, much better now. So that's one way to get the sharp crease. The other approach, which is not as robust as that, but in special cases can work well, is if we set, let's do vol all size 4, we can actually set a different mesh scheme, maybe of polyhedron, on this surface. And what it's done is now we have a quad that has its corner that's unshared is on this vertex. And that will be, that will now be a sharp crease. And so now we can specify a sweep of this volume from this top surface to the bottom surface, build U-spline vol 1. And again, I didn't have to set the U-spline because the defaults are degree 2 continuity of 1. Fit U-spline 1. And then if we draw this, we'll see we have that crease.
Greg, a couple of questions that have come up. So from Clint, the current process for building and fitting U-spline seems to demand that users perform these steps in a particular order. With the implementation of U-spline functionality into the GUI, will some of these steps happen without the need for the user to define them explicitly?
Yeah, as we move to a GUI, these, we kind of see a lot of these are like the low level commands that if you were to see the journal file, if you run some GUI command panel command, you would see these listed so that we give the user maximum control. But what you can expect is, and maybe similar to when we specified like this sweep here, there's like a workflow to specify this sweep. And if I say mesh this, right, the commands that actually get issued here, it actually submitted 5 commands when I hit mesh here. And I think you'll see a similar workflow in the GUI that it'll issue these multiple commands that you won't have to memorize them. They'll be provided to you through a GUI workflow. But then if you want to see them, to tweak them, you'll have them available to you because they will be journaled. So hopefully that answers your question, Clint. It's a very good question though, and thanks for asking it.
The question from Arik, can you go in reverse, build a U-spline with information, then export a CAD object spline for the output?
Sort of.
Did that yet? Have we, Greg?
So we sort of can. I'll show maybe a simple example of this. So maybe let me just in the sake of speed here, I'm going to use the shoulder again. I'm going to, if we say surf all, like it's going to mesh everything with quads anyways. If we mesh surf all, that's too many. Delete mesh. Surf all size 2 mesh surf all. What we can do is you can now say set U-spline surf all, and you could degree 2 continuity 1 build U-spline surf all as 1. And then we'll fit the U-spline. We have an export option, fit U-spline 1. We have a U-spline export option to step, but it's not actually a U-spline once we export to step. So export U-spline 1. So you see here, this is the step file, but we actually convert these to NURB patches and then export them as NURBS. So we can see like U-spline step output or step test. And now if we open up like a new session of Cubit, maybe I'll just, we can then import this step file. You'll see it's all just surfaces and some of the fitting. Oh, I forgot to crease groups. So sorry, I forgot an important command when doing surfaces. But the point is that you'll get out, this is analytic CAD with NURBS patches that have been converted from the U-spline. So apologize for this poor fit. I skipped a step by mistake, but that is technically possible, but it's no longer a U-spline at this stage. We are working to try to get U-spline supported in a native or a neutral format like step. It's something that we're working on. It's not a high priority for us at this time, but it is something that we are advancing.
Cool. So can you just tell us, so what's the step that you missed that would have made this look good, Craig?
Yeah, so the step I missed, let me remove U-spline all. So that's how you can remove a U-spline if you want to start back over. I forgot with surfaces, we build a U-spline crease group. This will eventually also be automated. It creates a group that we capture as an input to our U-spline commands to crease surface entities and like creased edges. So this has found automatically some creases that have been highlighted. And now if we build U-spline surf all as 1, fit U-spline 1. And now if I do this export, now it's got those creases. And what you could do from here, right, is you could you could now stitch these together. So if I go stitch, body all.
And this is also geometry you could send to a CAD modeler as well.
Yep, yep. And I can probably regularize some of this volume. So regularize the volume to, yeah. So maybe some of it won't regularize because they're not planar, they're all splines. So it may not be the best to work with. It's also only a boundary representation. It's not a volume. So it's only a surface.
Cool.
But, yep.
Greg, we've got a few other questions. I wonder if we should let you get pushing onto some of the
Yeah. Yep. Yeah. So let me move on.
Yeah.
Great questions though. A few limitations. I mentioned some of these. We only currently in 2021.11, we only support swept hex meshes. We also only officially support quadratic and cubic, so that's degree 2 and degree 3 bases. That means official support means we have unit tests that test these to make sure that they work. Our next release, we're targeting to go all the way up to degree 8, however. There's also a practical limit of about 10,000 hexahedral elements. Give or take, maybe we'll get away with like 80,000 or so, but we are addressing performance in our next release as well. We have primarily focused on getting capabilities up and running, and we're now going back and making performance work. We don't support T-junctions, although those are a feature of U-splines, and those will be something that we'll be adding in future releases. We also don't support the per element local variation of degree that U-splines support, but you can have different degrees on different non-conforming volumes. So disconnected regions can have different degrees. Something we're actively pursuing. Also, we're at extraordinary points, they're not smooth, they're just continuous. That's something that we've also been looking into. We have approaches, or we know ways to make them at least C1 smooth, but we haven't tackled that yet. And then lastly, I mentioned that semi-automated selection of curves to crease is only supported for surfaces. It's not supported for that volume like I showed previously. So now I'd like to quickly demonstrate an ANSYS LS-DYNA workflow. So you might have seen a demo of this, or kind of a quick run through of this in the 2 webinars ago. But let's talk about building a quality surface mesh on this volume. One thing you can see is that there's a lot of extra curves lying around that just come from the CAD representation. And what we might want to do is if we say that what we want to do is we're going to run a context simulation. But if you wanted to apply a boundary condition, maybe to like these faces, you have to have them creased around their boundaries. So I'm going to pretend that for this model, we're going to effectively hold a boundary condition on this highlighted surface, and then we're going to push on these 2 surfaces that you see here. So what I'm going to do is we have a kind of a nifty little command where I can select a surface and say select continuous. And it selects all the continuous surfaces within 1 degree of accuracy, of 1 degree angle of continuous. I can then hold control on my Windows machine and select to deselect these surfaces. And then, so I meant to be in my volume surface composite. And I've composited those into like a single macro surface. I'm going to also composite these surfaces. So again, I selected those 2 surfaces and hit select similar. I'm going to also composite these surfaces down here. So I'm going to select continuous. And select continuous here. For meshability purposes, I need to leave at least one of 2. I need to leave 1 dividing line. So I'm going to leave these 2 surfaces uncomposited. So now that I've done this kind of maximum compositing, this will allow Cubit to fit on a high quality meshes. And high quality with splines means few extraordinary points. Let me delete my mesh here. I'm going to choose a pave scheme. I like to use the extend option for the paver cleanup. I'll show you why. I'm first going to leave the default to on. Let's surf all size 10, I think is what we want to have. And let's mesh all of these surfaces. So this is a mesh here. At this stage, what I would recommend doing is assigning boundary conditions. One limitation with ANSYS LS-DYNA and the BXT format that we use is that blocks, side sets, and node sets, they're all sets, and you have to have unique IDs across all of the sets. So you cannot have block 1 and a side set with 1 and a node set with 1. You have to have like block 1, side set 2, node set 4, block 10. You just can't have these be duplicated. So we're going to say block 1, surf all. Could also have done that through the command panel here. I'm going to do that for the side sets. I'm going to create side set 2 so I don't clash with this block ID of 1. And I might call this side set name hold surf. And then I'm going to select this composited surface. And I'm going to say maybe side set 3. And I might call this push surface. And I'm going to select now these two surfaces. So now when we build our U-spline, it's important you do this before you build your U-spline so that our U-spline algorithm will capture that topology and then can export it as BEXT. So make sure you assign your boundary conditions before you create your U-spline. Now I mentioned just about the paver cleanup, extend versus on. If you just kind of look at, you can kind of see some of these extraordinary points. It's more efficient if you have fewer extraordinary points, which you can sometimes get through the extend option. So now if I delete the mesh and use this extend option, we'll find that we should get on the order of half of the extraordinary points of the previous mesh. So you can just kind of see here, there's more regions that are smooth. And so that's going to give us more efficiency in our solver. So again, I still have those side sets because they're defined on the geometry, not the mesh. So now what we would do is we would say set U-spline, surf all, degree 2, continuity 1, build U-spline, surf all. And while that's going, I'm going to show you just again, from time's sake and performance, that what we're going to do is we're going to be getting ourselves a BEXT output file. The DYNA cards option will also export a node sets or several node set K files that will define lists of node sets that you'll need to include in your model. And they will have names for the different kinds of cells that they have. So like side set 3, for instance. It'll also spit out this BEXT file, version 2.0, that LS-DYNA can parse. And what you're going to want to do is, in this case, I've got a main LS-DYNA K file. I'm just including my kind of part definition. It's an IGA kind of part here. And I'm using this keyword IGA include Bezier. I'm going to zoom in my text here so you can see this. And I can't remember exactly what these are. I know that this last ID here, you can look this up in the manual. This last ID is the dimensionality. So this tells it it's going to be a surface as opposed to a volume, which would be 3. I think this is in part ID. There's something else with that, but you can find this in the documentation for LS-DYNA under, if we search for star include IGA, or IGA, sorry, IGA include. You can find the information here. So I guess it's ASCII format, the part ID, you're assigning it surface or volume. As we've done here is we said it's ASCII format, part is gonna be 1, and we're gonna make it a surface. This section ID is also important. If it's an IGA part, when we go to the section, shell formulations. I need to find these up here. There is an element formula or an equation formulation here for isogeometric shells with NURBS. And so this is going to be important for us to set. So you can see here, we've got material ID. I think it's going to be, it might actually be in the next, in the next slide, but or the next file. So, yep. So here we go. We've got our section shell. The section ID is 1330, but then its element formulation is 201. And that's the same element formulation, whether or not it's a section shell or a section solid. So you can also export a solid volumetric U-spline to LS-DYNA, again, using this element formulation of 201. I think this command should probably be finished by now. I guess we're still building the U-spline. Again, performance isn't quite there. But again, if you do that U-spline export with that DYNA cards, that will give you these output, these files that you'll then load on to your LS-DYNA model. The last thing I want to show is using U-splines in Coreform IGA on an example, a more complex example.
So do you see the time, Gray? We've got about 10 minutes left.
Yep, I saw that. So maybe what I'll do is real quick, are there any questions with the LS-DYNA support before I move on?
Yeah, we had a technical. You go ahead and proceed.
Okay. So this is a model that I've derived from a model on GrabCAD. For those of you that are kind of our early adopter IGA partners, I'll be providing you this IGA example problem. So you can look for this shortly, just so you can test this out. And if you're interested, if you're listening to this and you're interested in trying this problem out, feel free to contact us at support@Coreform or sales@Coreform.com, and we can have some discussions. So this would be a very difficult part to build a hex mesh on. And even if we were to build a tetrahedral mesh, this model would require a lot of tetrahedral elements to build a mesh. And we may not want to spend that computational effort on the tetrahedral elements in our solver. And if you're doing a nonlinear solver, you may not even be able to get convergence with the tetrahedral elements that you might get out. So if I see if I can beat this is an ACES file. So instead of doing these body fitted meshes, here we go. So here's the tetrahedral mesh. Obviously the body fitted mesh we'd be doing, if we were doing hexahedral, we'd be defeaturing these fillets because it would be too difficult to build a body fitted hex mesh. The strategy with Coreform IGA is that we can instead build a partially immersing domain. So what I might do is I might create a bounding box of this volume. And then cut this volume just so it's cylindrical. So let's cut volume 1 by one of these outer radii on this rim. Let's delete this external volume. So just to get around some just numerical robustness issues that we're resolving, I'm just going to give a little bit of a scaling here of like maybe 5%.
Greg, I'll just note there are some questions that have come in about the hex meshing limitations for using IGA, and this directly addresses those issues.
Yep, exactly. And so now our mesh here, we can just do a simple mesh that's trivial to generate on this volume. And I'm just going to do a sweep now on this volume from front to back. And now this mesh is ready to have a U-spline built on it and run a simulation in Coreform IGA using the high order U-spline analysis. And so I've actually already run this in Coreform IGA, and I got results that I can show you. So just to show, this is the immersing U-spline for this model. Again, it's pretty much maximally smooth. The only extraordinary points, the only places it's not smooth are just a couple spots right around these extraordinary points. So it's pretty smooth. And if we turn off the U-spline envelope, we can see now the results. This is just displacement results on this. We're pretty close to having stress output on surfaces. We currently only export them to quadrature points. So for our solver right now, I'm just showing on the surface here.
So Greg, Hadi had asked if we could create U-splines for irregular geometries like human bones. I mean, there's a couple approaches. We could use the sculpt functionality, or this would be the other way of just immersing those.
Yep, exactly. Yep, that would, and especially if it's like maybe a bone that's got good structure to it, maybe like a ball and socket or something. You might want to do something that kind of aligns to the feature of it. If you've got like the actual, whatever the lattice structure is of a bone, I can't remember what they call kind of that foamy kind of structure. That's going to be pretty hard to do this kind of almost fitting approach. And you would probably just fully immerse that kind of structure inside of a bounding box, depending on what scales you're working with. But yeah, this is the approach. This is the IGA approach that is enabled by our U-spline technology. Again, the inherent numerical properties of U-splines allow us to do these nonlinear simulations in Coreform IGA with improved accuracy and robustness. So that's really the enabling technology here. But,
so Greg, we've got a few other questions, but have we kind of concluded the main part of the presentation now?
Yep, that's all I've got. So I'm ready for questions.
Okay. So Greg, first of all, thank you so much for your great preparation and explanation. And as participants drop off, we do have a one-question survey that you can answer, mainly just trying to decide, to understand kind of where you're at, if what you hope the next step is after you watch the webinar, if you want some support with trying out IGA and DYNA, or if you'd like to try out Coreform IGA with U-splines. And so if you can answer that, that would help us. And now we'll just answer questions for the next few minutes. So here's another question from Hadi. Higher order elements enable us to reduce the number of elements required to accurately build our geometries. I expect that this feature would also reduce computation time as we require much fewer number of elements. Is that true?
Yeah, so it's kind of partially true. Higher order elements do allow you to reduce the number of elements in that they converge at faster rates. So typically, like if you divide an element in half, the rate at which it converges to the solution is the degree plus 1. So linear elements converge at h squared, quadratics converge at h cubed, and so on and so forth. And so you do get this higher accuracy quicker. One of the challenges, though, is that a lot of traditional high order methods struggle with what's called conditioning of the linear system, which makes the linear system and any nonlinear systems that derive from it more difficult to solve, potentially. And so it may actually make, sometimes it may actually make them more difficult to solve by having high order elements. And that's why, especially in like explicit dynamic simulations, you don't really see quadratic hexahedra in codes like Abacus or LS-DYNA or these traditional HFEM codes because of those sorts of properties. So it's really it's the smoothness, the increased continuity of the U-splines in conjunction with the higher order that allows us to get the high accuracy more efficiently. So I see there's another question here about how the immersive U-spline works in simple words. It's hard to say simple, but what I would say is if you Google finite cell method, that is the method that we've generalized from, and it's a cut cell technique. And that can hopefully get you started on the right path. If you're interested in learning more, feel free to ask the question on our forum at forum.coreform.com. We can give you a more detailed response there. I just don't have enough time remaining to mention that. But thanks for the question. Also seeing, can mesh files be directly converted to U-spline in Coreform? Like if it comes from GMesh or HyperMesh? Currently, the mesh has to be created in Coreform Cubit. If you have a surface mesh of quads, it is possible. It's not officially supported, but it is possible to hack a surface mesh into U-splines, coming back into Cubit. We are working to generalize our U-spline construction so that we can handle more meshes. You'll see that coming in maybe the next year or so.
But again, the reason why that's the case is because we have to fit the U-spline to the CAD. And so that's
right.
We need the CAD connection.
Yep. Let's see. Limitation on material models in LS-DYNA. I don't know that I don't know if there are really limitations. We've only tested a few material models, but we have tested an elastic plastic material model. Our Cubit documentation, maybe I'll share that. If you go to our Cubit documentation, you'll eventually, in our U-spline section, we'll have the formats of BXT, and these formats will be defined here. But in our workflow section, so if you go to our user manual, Cubit workflows, and then there's this initial set of ANSYS LS-DYNA keywords that are supported. And we've got a kind of a sectioning of the ones that we've tested so far. But there shouldn't be any reason why they shouldn't all be supported, but just there's a lot to test. And we haven't tested them all. So, so VJ has asked about our typical time interval between major releases. I guess what I would say is that we wish we could be releasing all the time. We're kind of targeting what feels like a good cadence for us is somewhere around quarterly to maybe 6 months. But we don't have a set release schedules necessarily. Like you might be experienced with, like MATLAB always releases March, September. And we don't have that kind of cadence yet. But if you go to our downloads page, one thing that you can find is that we're always releasing versions of the day of Coreform Cubit in our latest development builds. And so when our pipelines pass on our development builds, we push these out to be able to download. And so if you're willing to be on the cutting edge and try out some things and report, user experiences or bugs to us, feel free to pull from the latest development builds to get new features.
And there'll be guidance for that on our form as well.
Yep. And then Herman has asked a question about the impact of numerical integration on higher order or very high order elements. And there's a couple of answers to that. One is that we can use traditional, if you're in a code like ANSYS or traditional finite element code that uses traditional Gaussian quadrature. You just build Gaussian quadrature on those piecewise components of the U-spline. And it's very simple, it's trivial to implement that kind of Gaussian quadrature. And again, the smoothness of the U-spline gives you good conditioning. The other is that in Coreform IGA, since we have access to the underlying spline representation, there's actually Gaussian quadrature is actually non-optimal in more than one dimension. So in 2D and 3D, it's non-optimal. And splines, there's actually, you can build optimal quadrature schemes. And we are working to build some of those optimal quadrature schemes into Coreform IGA. If you're interested, I think we might have on our homepage under Coreform IGA Research and Reports, under our Coreform reports, we do have some, you'll see here a paper from one of our former PhD students, or several of our former PhD students, on some of this efficient and robust quadratures for these splines. And so you might be interested to read through this. So you can actually view this document and read through it if you are so interested, Herman. So hopefully I can give you better answers than I can.
Okay. So. Well, Greg, thank you again so much for your preparation and your time in putting on the webinar. Thanks everyone for taking some time out of your day to attend and for the engagement. We appreciate especially all the questions. So again, feel free to answer the exit survey so we can know how to help you for the next steps.
And one last plug, please feel free to go to our forum and ask any and all the questions you might have that we couldn't answer on our forum here, and we'll try to answer them as quickly as we can.
Great. Okay. Well, thanks everyone. Have a great day.
Thanks everyone.